I think time to reconvene. So we have a remaining 45 minutes now for the rest of the session. There's going to be three speakers. I'm going to be the first speaker. I'll go for about 10 minutes. And then we have two remote speakers. The first one, remote speaker, will be Vladimir Starostin, who unfortunately can't be here today. He had to present remotely. And then Alexandros, who's going to be also calling in remotely. So there's a quick intro to RefNX and what we've been doing recently. I've got some stickers, so some merch. If anybody would like some stickers, please come take one at the end. I did have some, I was going to make some stickers for another package that, oh, got to wear that. It's like a special medallion. Yeah, anyway, so RefNX in a nutshell. Other people this morning gave demonstrations. Demonstration is going to be pretty hard because there's so much in RefNX, so much that you can do, lots of functionality, and demonstration might not give it justice. So whilst you read that, I'll pull some out of this slide. So mixed reflect models for incoherent averaging of patchy surfaces, using different components to model subset of an interface. So if you've got a particular structure that you want to implement, you can write a new component, and as long as you can render the slab representation of that, you can create your own models with physically relevant parameters. We have simulation of NR data sets, possibly in a slightly different way to what was being presented this morning in the other session. I wish I was at that one as well as this one. Different types of resolution fitting, stuff on clusters, batch fitting, and so on. Lots of stuff. If you want to get hold of RefNX, the code's on GitHub, where that's how you contribute your own changes if you want to make them. We have documentation on Read the Docs with lots of different examples for how to get started, frequently asked questions, how to install Python, how to install RefNX, use the GUI and so on. I have a video tutorial page on YouTube. I hate listening to my voice when I listen to it back on a video. Whenever I replay them in my mind, it's horrible. Anyway, and also a location where people can contribute your own code. And that's in something called RefNX models, similar to the SASView marketplace, I guess. So new features that we've been doing recently, because we've developed code for doing ellipsometry, we had to make energy dispersive scatterers, which should allow us to do something along the lines of resonant soft X-ray reflectometry. And the way that it does that is by querying the periodic table package for the particular wavelength of a material, and that will return a different scattering length density for each wavelength. As I said before, we've got different components. The one we use for polymer brushes is freeform volume fraction profile. That's what the VFP is. We've got some Maxent, stuff for doing lipid leaflets, splines, and so on. There's lots of really interesting stuff in there. I'll quickly talk about detailed resolution smearing kernel today, and other stuff. So we have different ways of using the various Bayesian analysis packages. So inbuilt to RefNX was the use of MC, so that's EMCEE, which historically has been the way that we've obtained those posterior distribution functions to understand the covariance and uncertainties in our system. We're now looking, I've got code examples on the website for how to use PyMC and Dynasty, which are also other Bayesian analysis packages. Of particular note for Dynasty is that it's very good for determining model evidence. So in the Bayes equation on the right-hand side, the denominator is the model evidence. And if you can calculate that for a specific model, you can use that to compare two models for which is more probable. It's also somewhat good at finding other modes in multimodal energy landscapes. So this is a demonstration of what you could do with, say, dynasty for model selection. On the left-hand side, we've got a couple of overlapping Gaussians. On the right-hand side, I've plotted the log model evidence as a function of number of Gaussians. So if you fit with 0 Gaussians, the model isn't very probable. You go to 1, the model is way more probable. Then to 2 is better still. And then 3, you don't actually get any more improvement. So that would be a 2 Gaussian system. And this might be useful for reflection. You know, is it a 1 slab system or is it a 2 slab system? Or for different, that would be an example of a nested model. But you can have 2 separate kind of structures and, you know, which one is the better one. And each of those has different speeds when it comes to getting a number of effective samples per second. I personally do a lot of work with detailed resolution kernels. This is going to be something that's important for DSS when it comes up. The reason for that is for time of flight reflectometer, the wavelength resolution is square. That's the middle graph on the left-hand side, but the angular resolution is trapezoidal. If your wavelength resolution is much wider than your trapezoidal resolution, you end up with something like on the right-hand side. So in the right-hand side, the black curve is a Gaussian resolution kernel. And that's approximating the true resolution kernel, which is the green one. So the green one is actually somewhat trapezoidal with a curved top. And those detailed resolution kernels can become really important when you're analyzing certain kinds of data. So if you're analyzing data near the critical edge or sharp features, yeah, that structure can become really, the actual shape can become really important. And one thing I'd like to happen in ORSO is being able to encode a probability distribution function like that on the right-hand side for each Q point. So that will happen eventually, fingers crossed. The other thing that RefNX can do is complex constraints, as well as bounds, simple box bounds. You can have describe your priors with any statistical distribution you like. You can have functional relationships between parameters or inequality constraints, which is super important. And this kind of inequality constraint or equality constraint is useful. That article there is really important. That's where we included those kinds of constraints in a physical growth model for a deposition of a small organic molecule. So one thing I've been coming into recently was maxent. So this is where you can freeform a model, a subset of a reflect, like a scattering length density profile with a much higher pixelated version, and you can employ an entropic constraint to smooth or regularize the data. I'm not going to go into this now because most of you should hopefully heard the full details of this. But suffice it to say that it's useful when you're unsure of what your initial model might be, or there's some kind of freeform profile. And lastly, is it lastly? No. Lastly, we have RefEllipse for analyzing ellipsometry data. You can co-refine ellipsometry, neutron, and X-ray data at the same time. Model creation is very similar to RefNX. And other optimizations we've been doing RefNX, lots of documentation, lots more examples. Jupyter notebooks, how do I do a functional form? How do I do this? Which are all on the website. Been optimizing the calculation kernels, got a kernel for automatic differentiation using JAX and improving it cluster compute speed. And so I think I've had 10 minutes, and we'll probably 1 more minute. Okay, 1 minute of question. Andrew. Oh.
So this is just something that's come to mind because you mentioned JAX, and it's something I've been thinking about for a few of the different. It was actually Jakin's talk earlier that made me think of it as well. Is anyone thinking about trying to do like properly probabilistic computing approaches to reflectometry analysis?
So I had a go at plugging the JAX kernel into the PyMC sampling. Because at the moment, there's two ways of doing it. You can use the JAX kernel, which makes the nuts sampler a lot, well, it's supposed to make the nuts sampler a lot faster. But when I was practicing, or when I was looking at it, that didn't actually make it any faster. It was actually still better to calculate derivatives with numerical differentiation.
Actually, I have a quick question.
Yeah.
If you've implemented the wavelength dispersive part for ellipsometry,
yeah.
Could you also implement it for a neutron SLD, a wavelength dependent?
It will already do it.
Yeah. Okay.
Yeah. So
there are some rare cases like gadolinium or which are close to resonance.
So instead of doing QR measurement analysis, you're doing theta wavelength R analysis.
Exactly. Yeah.
And it should possibly do X-rays as well, but there might be some more work to be done around the resonance points.
Okay, great. Thank you.
No worries. And it can also do non-spin flip analysis, but not spin flip. So now, if they're online, Vladimir, would you like to start sharing your screen?
Yes, thank you very much for having me. Can you listen to me? Can you hear me?
Yes.
Okay, perfect. So maybe I'll just share the whole screen. I hope it all works just fine, and please tell me if it doesn't, or you can hear me or you cannot see anything. And again, thank you for having me here. I hope and I know that some of you already were presenting in my talk on Monday. Unfortunately, today I cannot be presently with you because I got a bit sick, so I think it's more safe for everybody if I'm talking from campus here. But I'm very close, and I'm really happy to discuss all the things that we've been discussing all these days. So I will continue talking about machine learning in reflectometry, but more on the technical side and more with the software related problems. And if you were presented on Monday, you remember that I presented two approaches to reflectometry that we will be developing at University of Tübingen with many collaborators from Graz and Kiel, and together with Daphne and machine learning cluster in Tübingen. So the two approaches are, you can think about this at the replacements of the conventional algorithms. The first one is the replacement of the differential evolution algorithm, and this is called reflectorch, and this is going to be the focus of today's talk. And the other one is PANTE, the fast and reliable replacement for Bayesian inference methods such as Markov chain Monte Carlo. And I think here it is important to say what is the difference between the talks by the previous speakers and this one. And the main difference is that we are not developing new packages, but rather we're developing new algorithms. Of course, we have the software which I will present, but the main difference is that we don't want to make another reflectivity package because we see how many great packages already developed there, but rather we'd like to make some algorithms which can be shared and used by all the different packages with the different use cases, same way as differential evolutions, for instance, is used by all of these packages. And yeah, just to give some more context, especially for people who presented on Monday, the package Reflectorish I'm going to talk about today is the package that exactly was used in our closed loops experiments a year ago, published in paper. And this is the package which we use to precisely grow the films during the closed loop automatic experiments with predetermined thickness in different settings. Okay, so I will just go directly to GitHub, where you can, I hope you can see my screen still, right? This package is shared now on GitHub. You can download it, and many thanks to PhD student Valentin Munteanu from University of Tübingen, who put a lot of effort to make it more accessible for people so that you can already check it and try it out. Of course, it is a bit experimental because, of course, it's all the new algorithms. And I recommend you to install it from source. There is a great documentation here already. And of course, the initial idea of this package was to develop the code which is very flexible and fast for training new models for experiments. This is something which we did a year ago at the ESRF. And there is something which you can do for yourself, actually. So there is a page and documentation where you can look at and check how to train your own models. And it's actually quite simple. You basically have several methods you have to use. It's all, of course, requires some knowledge in Python, but I think we all use Python based on the previous talks, or maybe most of us. And there are some simple configuration files that one can use to provide their own use cases, constraints, parameter ranges, and so on and so forth. But I'm pretty sure that most of you are more interested in another part, which Valentin made accessible, is using already a trained model so that you can use it just from your laptop. You don't need any GPUs, you don't need any CUDA installed. You can just download a trained model and use it for your case. And this is one key difference between machine learning and standard conventional algorithms. And this is a technical challenge because, of course, you need the model for that. And the general wisdom is that you don't want to train one model which covers all the cases and such a big model that you cannot even then run it on you just don't have memory to run it on your computer. So instead, you'd rather want to train several smaller models which are used for some use cases. And this is what we are trying to do, and this is what we're aiming to do. And this is the repository on Hugging Face. And for those of you who don't know, Hugging Face is the first, maybe the leading, it's basically GitHub for machine learning models, so to say. So it's the place where you can freely put your machine learning models and then download very user-friendly style from your code and use directly. And currently we have here, I think, 70 models which are already trained for different use cases. And these models you can just use from the package. And of course, also it doesn't cover all the reflectometry, and especially the Newton part, we have to work on that a bit. And this is why I actually encourage you to approach me or Valentino or others and share your own use cases and your own models and what you would like to do so that we can train the model for you so that you don't have even to think about how to do that. We put it on Hugging Face and then you can use it straight away. And here's a quick demonstration about how we can use it. So the main method here is just inference model. So you provide the configuration name and the repository on Hugging Face, and it doesn't have to be this one, so we can make some more general repository for reflectivity. And the idea is that, again, we want to collect all the important use cases for you. And once you have that, this is the model which you can run on CUDA, but it doesn't have to be. You can just specify here CPU and run it on very simple laptop. So there are very limited hardware limitations. So it's very easy to run. And you see there is some information here which summarizes the model which you just downloaded with different parameter ranges and other settings that are important for like how the model was trained. And once it's done, you need two things. You need experimental data and you need parameter bounds for your particular curve. So the model, I explained it on Monday, but maybe just repeat it now that the model is trained on a large range of parameters, but it takes into account your physical knowledge, prior knowledge for every particular curve. So you can specify the parameters, the parameter ranges, and the model prediction will be within those parameter ranges. And it is blazingly fast. So I'm now working like with my laptop, which I think it's CUDA, but it's a very simple CUDA, and it's done basically instantly. So you can see this now I run the prediction and it's super fast. Now, this is all good, but one thing I'd like to put attention to is something which conventional analysis is not really interested about, but it's very important in machine learning. And this is something we call unit invariance in reflectometry. And the idea is that if you think about the parameters of that come in as an input to your reflectometer simulator, the reflectometer engine, Q values, thicknesses, roughnesses, SLDs, you can scale them. You can rescale them to achieve the same curve, but for different Q values. So the idea is that your Q values are, let's say, in inverse angstroms, thicknesses are in angstroms, sharpnesses in angstroms, SLDs are inverse squared angstroms multiplied by 10 to minus 6, it doesn't matter. So you can now use some scaling coefficient to change these units, let's say 2. And as a result, you get Q range, which is changed by the curve stays the same. And here it is demonstrated a bit better. So you can effectively squeeze the Q range. And this allows you to use the same model, which is trained on one Q range, but for very different Q ranges during inference. And this gives you great flexibility, but at the same time is a challenge because you have to kind of figure out which parameters can you use, which models can you use, because there is this flexibility resulting from scaling invariance. So to summarize, this is the package that you can already use. I would be really happy if you can give us some feedback. It's a bit experimental, of course. It's been put on GitHub just a week ago, maybe less than a week ago. And yeah, thank you very much.
Does anybody have any questions for Vlad? Or should we move on? So Vlad, I have one question. The models you upload to Hugging Face, I noticed they're all pickles. Are there any other ways of serializing that other than pickle for security purposes?
Yes, I believe there are different ways to do that, and you don't have to use Pickle. I'm not sure if actually the ones which are uploaded by Valentina Pickles. Yeah, there are, but yes, you're right. But in general, yes, of course, you can do that in a more kind of cross-platform way. And this is a bit experimental now, but yes, of course, it's very standard interface, let's say, for sharing the models. So it's in general pretty safe, yes.
Are there any other questions that Norifumi?
Thank you for the nice talk. I have a question concerning the machine learning. as far as I understand, the machine learning is a kind of the interpolation. But if the experiment is out of the, how to say, the parameter space we did for the machine learning, so what happens if in such a case? Or my understanding is incorrect?
Excuse me, you're asking what happens if the parameter ranges that you would like to provide to the model are out of the training ranges, right?
Yeah, training range.
Yeah, so basically there are two possibilities here. First, as I tried to explain very briefly, there is this unit scaling invariance in reflectometry that might still give you the way to squeeze your experimental data in the parameter ranges, and that might be done, let's say, by using only a part of the Q range, and then you can rescale the parameters using this invariance. But this is the one approach, and if it doesn't work, of course, you have to retrain the model. And partially what is also kind of one of the way to optimize the process is that the encoders for the machine learning model can be separated from the predictors. And just to make it more kind of clear, there is a part of the model which encodes the reflectivity curve, and this can be much more flexible. So this just has to extract some features from the reflectometry curve. It doesn't have to necessarily be within the parameter ranges. And then there is a much more shallow regressor, and this regressor has to be retrained. And if you already use the pre-trained feature extractor, which we can also, of course, provide, then it's going to be much faster and simpler to retrain the model for you.
Thank you. So we'll now move on to the next presenter, Alexandros Koutsioumpas.
Yep.
I'm not sure if that's if I
It's
used your
fine.
name there.
Use my first name, it's fine. It's perfectly fine. So I will just share my screen. Just a moment. On the keynote here. Good. So you can see the presentation?
Yes.
Good, perfect. So greetings from Munich. Unfortunately, we had a PhD defense this week and I couldn't join you at the conference. So I will just briefly speak about Anaklasis, the package that I develop. So the package was released around 2021, together also with a related publication describing a bit the methods that were used. So essentially, it's a Python code with a calculation engine in Fortran or Numba for speed. Large parts of it are inspired, of course, by RefNX, by Ref1D and Aurora. The user base currently is around 10 to 15 PhD or postdocs that mainly work with reflectivity data, and I'm talking mainly about the people also who provide feedback. And the main idea that also differentiates a bit the package comparing to other packages is related to model definition, as I will describe in detail later. And also an emphasis is given on making it easy to work with multi-contrast data, and also to make it easy to use MCMC or other methods for estimating parameter covariance. So a few basic details. First, you can find the code in GitHub repository. Here is a QR code for it, where you can find also a manual and the API, and also quite a few Jupyter Notebook examples where you can see a bit in action how, especially in relation to data fitting, how the package works. Also, if you don't want to install it, there is also the possibility to run it on the cloud through Binder if you want to play around a bit with basic stuff. Installation unit tests are also included, and also the package, the calculation engine is tested weekly by the ORSO validation tests. Now, the motivation for writing the package came from some practical needs, because I'm an instrument scientist, so we have users who try to fit data. So in many cases, we had users where they were familiar with packages like MotoFit. Most of our users were using MotoFit. And in the case where they had, simple systems that could be described by slabs, that was okay for their needs. They were fitting the data, they were happy. The problem was coming in the case where they had a bit more complicated systems and they wanted to include some functional dependencies in their system. So for this reason, in Anaklasis, we use a mixed way of defining slabs, both, so that the parameters of the slabs can be either numerical values or we can use directly expressions in the model, as I will show. Also, you can describe constraints between the parameters as simple inequalities in the program. And also, we include a simple way for performing MCMC or bootstrap analysis. And also, through the use of multi-parameters, we make it easy also to, we streamline the multi-contrast fits. So, in order to explain how this works, so in the simple case where we have a two-slab system and we want to calculate the reflectivity, we define the model as a list in Python, where its, let's say, layer is a list in itself, a succession of real SLD, imaginary thickness, roughness, as, let's say, as you would expect also from, as it is done also in other programs. And you see here for the simple case, we just define the model, some parameters for the instrument. We call the function that calculates the reflectivity and we get our answer. Now, imagine the case where you don't have such a simple system. Imagine the case where you have some measurements from a polymer brass system. We know that in the case of polymer brasses, at an interface, we have a functional dependence of the SLD as we move away from the surface. So in order to define the model for such a system, we can, as you see here, define first our substrate, thin water layer, and then we define an expression for the evolution of the SLD as we move away from the system. And the next 10 layers we insert this expression for the SLD directly into our model. And in this way, we are able here in this particular case to fit the data from a polymer brass system. As you see, our expression here contains some parameters that are defined here later, where we can define, of course, the range where the parameters can vary, and also if they have a prior uniform or normal distribution. Also, by simply here stating that you want to do an MCMC step after the fit, you can also estimate quite simply the correlation of the parameters that were defined in the model. Now, in a more elaborate and a bit more, let's say, well-known example, in the case of a supported lipid membrane, for example, you see again in our model, we define our substrate, the silicon oxide, water, and also our supported lipid bilayer as 4 different layers. Now, in the case where we want to correlate the molecular volume and the area per lipid of its leaflet to the SLD and the water content, we have some relations that give us this dependence. So we can insert essentially these functional dependencies of the SLD and the solvent volume fraction directly here in our model, with expressions that depend on parameters that are either fixed or left to vary depending on the type of fit that we have in mind. Also, for the case, in the case where we have multiple measurements with multiple solvents of multiple contrasts, we define the multi-parameter for the simply the solvent as a multi-parameter, where for each curve we have a different set of ranges for the SLD of the solvent. Also, for this particular system, during our fit, we know, for example, that the solvent volume fraction cannot go below 0, so we can put this constraint here at the end simply as an inequality that is taken into account during the fit. Here you see the result of the fit for the model that was presented in the previous slide for 3 different contrasts, and also here the results of the MCMC step, where we see that the only correlation, let's say appreciable correlation that we have is only for a set of parameters. So that's simply a few words about the package and what differentiates it from other packages. You can, if you are interested, you can scan the QR code, go to GitHub and have a look the Jupyter notebooks for many different examples of the use of the package. Thank you.